If you had been alive 250 million years ago, you could have walked from what is now the Sahara Desert to what is now the Appalachian Mountains of West Virginia without ever seeing the ocean. You could have crossed, on foot, from the modern position of Cape Town to the modern position of Barcelona. Every continent you know, every coastline, every country, every stretch of sea between them was a single connected landmass, a single body of rock and soil wrapping itself around one side of the planet, surrounded by one ocean that wrapped around the other. The coastlines that you picture when you close your eyes and imagine a map of the world, the shapes of Africa, of the Americas, of Europe, of Asia, of Australia, of Antarctica, none of them existed. There was only one continent, given to it much later by the German meteorologist and geophysicist Alfred Wegener, was Pangaea. The word from the Greek means simply all lands or whole earth. And for roughly 100 million years, across the late Permian and early Triassic and into the early Jurassic, it was exactly that. Every piece of land on Earth above sea level was part of the same enormous body. Across the next 200 million years, it tore itself apart. This is the story of how, not the story of the arrival of a single disaster, not a meteor, not a climate shift, not an extinction. The breakup of Pangaea is instead the slow, patient, unavoidable consequence of the physics of a planet that has too much continental rock assembled in one place. It is the story of how a landmass, entirely by its own internal dynamics, opened itself into seams and then opened those seams into oceans across tens of millions of years, pushed those oceans wide enough to become the geography we now know. The world you live in, the 7 continents, the 5 oceans, the specific shapes of coasts and mountains and seas, is what is left when Pangaea finishes falling apart. Some of it is still falling. To understand how Pangaea ended, you first have to understand how it began. Pangaea was not the first continent. It was not even the first supercontinent. It was, in fact, one in a sequence of large landmasses that have assembled and broken apart across more than 2 billion years of Earth's history. Geologists call this the supercontinent cycle. The rough periodicity, from the formation of one supercontinent to the formation of the next, is somewhere between 300 and 500 million years, though the cycle has been longer or shorter at different points in Earth's history, and the evidence for the earliest supercontinents is fragmentary. Before Pangaea, there was Rodinia. Rodinia formed roughly 1,100 million years ago, during the late Mesoproterozoic, and persisted as a single mass until about 750 million years ago, when it began to break apart. Before Rodinia, there was possibly another supercontinent called Nuna, somewhere around 1.6 billion years ago. And before Nuna, there may have been earlier configurations still, whose evidence is now too deeply buried or too thoroughly recycled for us to reconstruct with confidence. What connects all of these is a repeating geological rhythm. Continental plates, drifting on the slow currents of the mantle beneath them, tend over long enough times to collide. When they collide, the crust thickens along the suture zone. Mountain belts rise. Some of the highest and most dramatic mountain ranges in Earth's history are the scars of these collisions. Eventually, after enough collisions, a large fraction of the planet's continental material ends up in one place. A supercontinent exists. Pangaea's formation began in earnest in the late Devonian and early Carboniferous, about 350 million years ago, when the continent of Laurussia, itself the product of earlier collisions between Laurentia, Baltica, and Avalonia, began to close in on the southern supercontinent of Gondwana. Gondwana, at that time, consisted of what are now South America, Africa, India, Antarctica, Australia, and Madagascar, all already joined into a single large mass. The closing between these two across the Reich Ocean that had separated them produced the Appalachian and Variscan mountain belts. The remnants of these mountains, in places like the Smoky Mountains of Tennessee and the highlands of central Germany, are still visible today, far from any modern plate boundary, as the deep roots of ancient origins. By about 335 million years ago, the main continental masses had joined. Over the next 50 million years, through the Middle and Late Carboniferous and into the early Permian, other smaller blocks continued to collide along the edges. Siberia joined the east, Kazakhstan joined the north. By 280 million years ago, in the Middle Permian, the assembly was essentially complete. Pangaea, as a single landmass, was finished. It stood fully assembled for something like 80 million years, through the late Permian, through the Triassic, into the earliest Jurassic, before the first clear signs of its breakup began to appear. The shape of Pangaea was striking. It was, very roughly, a crescent, or a fat letter C, depending on which reconstruction you favor. The western side of the continent, corresponding to what is now the Americas, extended from approximately the latitude of modern Alaska down through equatorial regions and into the southern mid-latitudes. The eastern side, corresponding to what is now Europe, Africa, and the eastern arc of Asia, extended across similar latitudes, but with a notable embayment in the middle. This embayment, opening eastward into a shallow sea, was called Tethys. Tethys in the Triassic and Jurassic would be a long, shallow tropical sea, the ancestor, in the broadest sense, of the Mediterranean. Beyond the continent, in all other directions, was a single enormous ocean called Panthalassa. Panthalassa covered perhaps 70% of the Earth's surface. It was vast, deep, and largely undifferentiated. You could have sailed from the modern Pacific, out past what is now Asia, around past Australia, along the edge of what is now South America, and back to your starting point, without ever crossing the boundary of a separate ocean basin. It was one body of water covering 2/3 of the planet. The shape of the continent had consequences. A single enormous landmass stretching from pole to equator to pole produced climate patterns that no modern continent reproduces. The deep interior of Pangaea, thousands of kilometers from any coastline, was profoundly arid. Moisture from Panthalassa or Tethys had to travel enormous distances before reaching the center of the continent, and most of it rained out before it got there. The result was one of the largest continuous desert belts in the history of Earth, stretching across the interior of what is now the Sahara, Europe, Central Asia, and out through what would become the North American West. The red beds of the Permian and Triassic, the famous reddish sandstones that characterize rocks of this age across half a dozen modern countries, are the sediments of that vast desert. Along the coasts, the climate was wetter. Monsoonal circulation patterns, driven by the extreme thermal contrast between the continent and the ocean, produced strong seasonal rains. Tropical forests grew along the margins. Temperate forests in the higher latitudes extended down to the shore. Polar regions of Pangaea, particularly the southern parts that corresponded to modern Antarctica, Australia, South Africa, and southern South America, supported cool temperate forests whose remains are preserved in Glossopteris floras, the ancient broad-leaved seed plants that distinguish Gondwanan rocks from rocks of equivalent age in Laurussia. The Permian world, then, was a world of extremes, a vast inland desert, a long tropical coast, polar forests that received months of continuous darkness and then months of continuous light, a single ocean so large that it took weeks to sail across, an atmosphere whose circulation patterns no modern planet possesses because no modern continent has that shape. This was the stable state Pangaea held for millions of years. Life on a single continent took advantage of the geography in specific ways. A creature that evolved anywhere on Pangaea could, given enough generations, walk to any other part of Pangaea. There were no ocean barriers. A hungry carnivore, born in what is now Brazil, could slowly, across generations, across tens of thousands of years, expand its range up through what is now Africa, through Europe, across Asia, and down into what is now Australia. The dinosaurs and proto-mammals of the late Triassic and early Jurassic, the lineages that emerged after the end Permian extinction and began to repopulate the ecosystems, did exactly this. Found on every modern continent, form a single connected global fauna with relatively minor regional differences. The same dinosaur genera appear in North American rocks and in African rocks. A large Triassic archosaur is found in Brazil. Its close relatives are found in Europe. The animals of early Pangaea were one biota with a vast shared range. Certain plant groups tell the same story. The Glossopteris flora, distinctive of the southern portions of Pangaea, is found in what are now India, Antarctica, Australia, Africa, and South America. These plants are, as far as we can tell, a single coherent southern vegetation that was distributed across all the southern parts of the continent in the late Paleozoic. The fact that identical plant fossils appear on 5 modern continents, separated by thousands of kilometers of ocean, is one of the clearest lines of evidence that those continents were once one body. Freshwater animals, creatures that could never have crossed a saltwater ocean, show the same pattern. A small aquatic reptile from the early Permian is found in freshwater deposits in South America and in southern Africa, and nowhere else. It was a creature too small to swim across an ocean and too specialized for fresh water to survive in the open sea. Its presence in those 2 specific places and nowhere else is explained if and only if South America and Africa were a single connected landmass with a shared river system. All of this, the flora, the fauna, the distribution of particular species, was known to Alfred Wegener. When he proposed in 1912 that the continents had once been connected, he did so on the basis of exactly this evidence. He did not have plate tectonics. He did not have paleomagnetism. He did not have seafloor spreading. What he had was the matching of coastlines and the distribution of fossils, and a conviction that these patterns could not be accidents. The pattern was too coherent, too repetitive, too precise. Something had connected these places once. What Wegener did not have, and what would ultimately cost him his acceptance by the geological establishment for decades, was a mechanism, a reason, a physical, plausible, workable explanation for why continents might move. Wegener was not a geologist. He was trained in astronomy, had done meteorological work in Greenland, and was by vocation a polar explorer. His proposal of continental drift was, in a sense, a side project, the kind of hypothesis an outsider can make, unencumbered by the weight of a discipline's received wisdom, but also unsupported by its institutional machinery. The evidence he assembled was, by any neutral reading, substantial. The fit of the coastlines of South America and Africa was not a vague resemblance. If you overlapped them, you could match specific features. The bulge of West Africa fit into the curve of the eastern Brazilian coast. The square projection below Namibia matched the inward corner below Uruguay. The match was accurate not just at the modern shorelines, but along the continental shelves, the submerged true edges of the land masses. When these true edges were used instead of the modern water margins, the fit was, in places, essentially exact. He cataloged the fossil correspondences: Mesosaurus, Glossopteris, Synagothus, a Triassic therapsid, the pig-like survivor of the end Permian. All of these creatures appeared on continents now separated by deep oceans, in rocks of the same age, with no plausible mechanism for transoceanic dispersal. He cataloged geological structures that crossed modern ocean boundaries, mountain belts whose sedimentary and metamorphic histories matched on opposite sides of the Atlantic. Coal beds in Antarctica, a place that today sits at a polar latitude and is covered in ice, whose fossil record of Glossopteris meant that Antarctica had once sat at temperate latitudes. Striations on rocks in India and in Brazil and in southern Africa, all pointing the same way, all indicating that a single ice sheet had, in the late Paleozoic, covered those now widely separated regions when they had been joined as one southern continent. The evidence was, in retrospect, overwhelming. But Wegener could not explain how. He proposed, at various points, that centrifugal force from Earth's rotation or tidal forces from the Moon might have pushed continents across the ocean floor. Physicists and geologists who ran the numbers on these proposed mechanisms found them wildly inadequate. The forces Wegener suggested were, by orders of magnitude, too weak to have moved continental masses through solid oceanic crust. And so, across the 1920s and 1930s, his hypothesis was rejected. Most geologists continued to believe, as they had for decades, that the continents were essentially fixed. The fossil correspondences Wegener had catalogued were explained instead by long sunken land bridges, hypothetical strips of land that had once connected continents and had since subsided into the ocean. This was, as we now know, wrong. But it was an explanation consistent with a geology in which continents did not move. Wegener died in Greenland in 1930 on a supply mission during an expedition. He was 50 years old. His hypothesis of continental drift had been published for almost 2 decades, and it was, at the time of his death, considered a curiosity of the history of science rather than a living idea. It would take another 30 years, and a very different line of evidence from the ocean floor, for the geological community to return to what Wegener had proposed and find, finally, that he had been correct. The confirmation came from the sea floor. In the decades after the Second World War, as naval sonar technology was turned to peacetime use and oceanographic research expanded worldwide, a picture of the seafloor began to emerge that had never been available before. Ship-based bathymetric surveys mapped the topography of the ocean bottom in increasing detail. Magnetic surveys, towing sensitive magnetometers behind ships, measured the strength and direction of the magnetic field embedded in the rocks of the ocean floor. Seismic surveys, using controlled explosions or natural earthquakes, probed the structure of the crust beneath the sediments. What this work revealed through the 1950s and early 1960s was something nobody had quite expected. Running down the center of every major ocean basin on the planet, a chain of underwater mountains, the Mid-Atlantic Ridge had been known in vague outline since 19th century cable-laying surveys. But the full extent of the world-spanning ridge system and its internal structure were only properly mapped in the post-war period. By the early 1960s, oceanographers understood that a continuous chain of mid-ocean ridges ran for some 65,000 kilometers across the floors of every ocean, from the Arctic to the Antarctic, through every major basin, a single enormous underwater mountain system snaking around the planet. And running along the crest of each of these ridges, there was a rift valley, a central depression, sometimes kilometers wide down the middle of the ridge, where the topography dropped sharply and where the rocks were unusually young, volcanic, hot, active. The rocks on either side of the rift, as you moved away from it, grew progressively older. This was one of the key observations. The youngest oceanic crust, the youngest basaltic rocks on the sea floor, were always along the crests of the ridges. The older the rocks, the further they sat from any ridge. The oldest oceanic crust in the world, about 200 million years old, was found along the continental margins of the old ocean basins, far from any ridge at all. The explanation, proposed by the American geologist Harry Hess in 1962, was what came to be known as seafloor spreading. Hess suggested that the mid-ocean ridges were places where new oceanic crust was being created, where magma from the mantle below was rising, solidifying, and forming new rock along the ridge crest. As more new crust formed at the ridge, the older crust, already made, was pushed aside. The result was a slow conveyor belt of rock moving away from the ridge on either side. The ocean basins on this view were not ancient features. They were growing constantly by accretion at the ridges, and the continents that bordered them were not fixed. They were being pushed apart slowly by the expansion of the ocean basin between them. The hypothesis was elegant. It explained the pattern of ages, the pattern of heat flow, the distribution of volcanism. But what confirmed it, and what turned the geological world upside down within a decade, was the magnetic evidence. Every few 100,000 years, for reasons rooted in the dynamics of Earth's molten outer core, the planet's magnetic field reverses. North becomes south. The field does not disappear, it simply flips, but during the brief interval of the reversal, rocks cooling from the molten state into solid rock freeze their iron minerals aligned with whichever direction the field is currently pointing. A basalt erupted during a normal polarity epoch will carry an embedded magnetic signature pointing one way. A basalt erupted during a reversed epoch will carry a signature pointing the opposite way. And once the rock has cooled and solidified, its magnetic signature is locked in, unchanged by subsequent reversals of the field. In the early 1960s, magnetic surveys of the seafloor on either side of mid-ocean ridges revealed a pattern of striping, parallel bands running along the ridge with alternating magnetic polarity. Normal, reversed, normal, reversed, normal, symmetrically on both sides of the ridge crest. The pattern of stripes on the western side of the Atlantic matched almost exactly the pattern on the eastern side. It was as though the sea floor were a magnetic tape running from the ridge outward on both sides, recording the history of Earth's magnetic field. In 1963, the British geophysicists Fred Vine and Drummond Matthews, and independently the Canadian Lawrence Morley, published the interpretation that clinched the case. If seafloor spreading was real, then the crust along the ridge was being produced continuously. If the planet's magnetic field reversed periodically, then the newly formed crust at the ridge crest should, over time, record those reversals as parallel stripes. And the symmetry of the stripes on either side of the ridge should reflect the fact that new crust was forming on both sides simultaneously. The predicted pattern was exactly the pattern the magnetic surveys had found. By the late 1960s, the synthesis of seafloor spreading, the magnetic anomalies, the patterns of earthquake force at ocean trenches and ridges, and the behavior of the lithosphere as a set of rigid plates moving over a more plastic mantle beneath, had fused into what is now called plate tectonics. It was the single largest revolution in the earth sciences in the 20th century. And it validated, explicitly and with overwhelming quantitative evidence, what Wegener had proposed half a century earlier on the basis of maps and fossils. Continents did drift, and they drifted because they were riding, as passive features on top, a dynamic mantle system that was actively moving them. But why do continents break apart at all? Why does a perfectly stable supercontinent sitting calmly on a section of the mantle begin, after 100 million years of stability, to tear itself open? The mechanism that most geologists now favor is, in a simplified form, as follows. The mantle beneath a large continental mass behaves differently from the mantle beneath an ocean basin. Continental crust is thicker, typically 30 to 40 kilometers, compared to oceanic crusts 6 to 10, and it is compositionally different, richer in light minerals that do not conduct heat as well. When a large volume of continental crust sits in one place for a long time, it acts in effect as a thick insulating blanket over the underlying mantle. The heat produced by the mantle, which would normally escape upward through the crust, is partially trapped. This was pointed out explicitly by the geophysicist Don Anderson in 1982. A supercontinent, by virtue of its size, insulates a much larger area of mantle than any smaller continent does. The heat that would, in a normal configuration, escape through the ocean floors is, beneath a supercontinent trapped under thick continental rock. Over millions of years, this trapped heat accumulates. The temperature of the mantle under the supercontinent rises. Eventually, it rises enough to initiate new convective plumes, upwellings of hot, buoyant mantle rock that rise toward the base of the crust. These plumes, when they reach the underside of the continent, do two things. They provide a direct source of magma, which can erupt as enormous flood basalts, and they mechanically stress the overlying lithosphere, pushing upward and outward, trying to split it from below. If the plume is large enough and persistent enough, it can break the continental crust along a line of weakness, often an old suture from an earlier collision, or a line along which the crust is already thinnest, and open a rift. The rift, once opened, eventually connects with the global mid-ocean ridge system. New oceanic crust begins to form in the gap. The supercontinent, which was one piece, becomes two. The insulation hypothesis makes a specific testable prediction. If supercontinents break up because they trap heat beneath themselves, then the time from the assembly of a supercontinent to its first major rift should be roughly the time required for that heat to build to the threshold required for plume generation. Different models give different answers, but a consensus estimate is something like 50 to 100 million years of stable assembly before the first major rift. Pangaea's interval from full assembly around 280 million years ago to the first major camp eruption around 201 million years ago is about 80 million years. This fits the predicted range. Rodinia, similarly, appears to have held together for perhaps 100 to 200 million years before its first breakup. Both data points are consistent to within the uncertainty of our dating with the mantle insulation mechanism. There is another complementary factor. Once a supercontinent has been assembled long enough for mantle convection beneath it to reorganize, the pattern of sinking and rising mantle material, the so-called geoid, favors particular locations for plume generation. These locations are typically above deep mantle anomalies called large, low shear velocity provinces, which sit above the core mantle boundary beneath the Pacific and beneath Africa. Plumes rising from the edges of these LLSVPES tend to anchor in stable positions across long time scales. As continental plates drift across the surface, the plume locations remain, roughly, where they were. When a continent finally comes to sit over a plume, the interaction can initiate rifting. Pangaea's breakup in this light was a combination of factors. Mantle heat trapped beneath the continent for 80 million years, plume activity rising from deep mantle anomalies, old zones of crustal weakness inherited from earlier collisions. At the moment, the camp plume arrived under what is now Northwest Africa and the eastern seaboard of North America. The combination of those factors was enough to crack the crust open. This is, we now understand, roughly what happened to Pangaea. The continent had been assembled around a long history of collisions and sutures. It carried in its interior a dozen ancient scar lines where earlier continents had come together. Some of these were weak, others were relatively strong. But the cumulative heating of the mantle beneath the entire landmass across 80 million years of stable assembly eventually drove the system to a threshold. At that threshold, a plume pushed upward beneath the eastern coast of what is now North America and the western coast of what is now Northwest Africa. It reached the underside of the crust, it began to erupt, and the first chapter of Pangaea's breakup began. The event is called the Central Atlantic Magmatic Province, usually abbreviated CAMP. It occurred 201 million years ago at the end of the Triassic period, and it is, by several measures, one of the largest flood basalt events in Earth's entire history. If you could have stood at the time, somewhere in what is now Morocco, or on the coast of what is now New Jersey, or in what is now the western Amazon basin, or along the edge of the Bay of Biscay, in what is now France, you would have seen, over a span of perhaps 600,000 years, an unthinkable volume of lava rised to the surface and spread. Fissures opened along a north-south axis that would eventually become the seam of the Atlantic Ocean. Basaltic lava poured from them in sheets that sometimes covered thousands of square kilometers at a time, advancing slowly enough that the flow edges cooled and the liquid interiors continued forward. The total volume erupted across all the separate pulses is estimated at approximately 4 million cubic kilometers of basalt. The total area covered exceeds 11 million square kilometers, larger than modern Europe. The basalts erupted in what was, at the time, a single connected region at the heart of the still assembled Pangaea. Today, because of the subsequent breakup, the remnants of that single eruption are scattered across 4 continents. Basalt flows related to Camp are preserved in the Anti-Atlas Mountains of Morocco, in the Amazonian Basin of Brazil, in the Fundy Basin of Nova Scotia, in the Newark Basin of New Jersey and Connecticut, in the Mesozoic basins of Portugal and Morocco, in the basement rocks of Iberia. The reconstruction of a camp source region requires assembling these 4 scattered territories back into their original single arrangement, fitting them together the way Wegener and his successors fit the coastlines. The volcanic and atmospheric consequences of camp were, as one might expect from such a scale of eruption, enormous. Carbon dioxide released by the eruptions raised atmospheric greenhouse levels significantly. Ocean acidification followed. Sulfur dioxide produced short-term cooling pulses, alternating with longer-term warming. The climate across the end of the Triassic was severely disturbed, and the biological consequences were correspondingly severe. The end-Triassic extinction, which ended the world of early archosaurs and opened ecological space for the dinosaurs that would dominate the next 135 million years, was contemporary with the camp eruptions and is widely believed to have been caused, directly or indirectly, by them. Roughly 50% of marine genera disappeared at the end-Triassic boundary. Conodonts, a long dominant microfossil group, ended entirely. Many reef-building groups collapsed. On land, many of the earliest mammal-like reptiles died out, as did a large fraction of the non-dinosaurian reptiles. The ecosystems that reorganized after the extinction were dominated by the surviving dinosaur lineages, which diversified rapidly in the early Jurassic into the classical dinosaurs of the Mesozoic. But beyond the biological catastrophe, camp had a geological legacy that continues to this day. It was the beginning of the Atlantic Ocean. In the aftermath of the main camp eruptions, the rift that had produced them did not close. The crust along the line of fissures had been thinned, weakened, and thermally softened by the plume activity beneath it. As the overall stress field of the region continued to pull the 2 flanks of the continent apart, North America on one side, Africa on the other, the rift deepened and expanded. At first, for millions of years, the widening rift was filled only with lakes, with river systems, with alluvial fans draining into closed basins. The Newark Basin of the eastern United States, which is now a series of small sedimentary basins threading up through New Jersey and Connecticut, was then a large rift lake system, hundreds of kilometers long. Similar lake systems on the African side and on what would become the Iberian and Moroccan sides filled their own parallel basins. Dinosaur footprints preserved in the sediments of these rift lakes record terrestrial animals still wandering across the gradually separating continents. Fish, preserved in the lake sediments, include species that appear on both sides of the rift, because the 2 flanks had not yet fully separated. By about 180 million years ago, roughly 20 million years after the initial camp eruptions, the central rift had reached the stage where it was below sea level, and marine water, spilling in from the existing Tethys and Panthalassa systems, had begun to occupy it. The rift at this stage was a narrow, elongate sea, perhaps as wide as the modern Red Sea. Salt deposits from evaporating seawater in restricted parts of the rift preserved now in the Atlantic continental margins on both sides, record these early marine conditions. By about 170 to 160 million years ago, the connection had widened enough to allow substantial open ocean circulation. The Central Atlantic Ocean, in recognizable form, existed. It ran from the Tethys on its northern end, southward in a long, narrow corridor, down to the equatorial regions where, at that time, no southern extension yet existed. The North American plate, carrying what would become the eastern seaboard of the modern United States, was moving westward, away from the African plate. The spreading rate in the early stages of ocean opening was fast, probably 5 or 6 centimeters per year. The rate has varied considerably over the subsequent 170 million years, sometimes slowing, sometimes accelerating, but it has never stopped. The Mid-Atlantic Ridge, that chain of underwater mountains running down the middle of the Atlantic, is the continuing edge of the spreading zone. Every year, a few centimeters of new oceanic crust form along it, pushing North America and South America westward, pushing Europe and Africa eastward. The continents that Wegener had matched, the bulge of West Africa against the curve of Brazil, the square of Namibia against the corner of Uruguay, had, in the early Jurassic, just begun to separate. Over the next 160 million years, they would move further and further apart until the Atlantic Ocean, in its modern form, stretched 11,000 kilometers between them. That process, quietly, is still running. While the Central Atlantic was widening, the rest of Pangaea had not stayed still. Gondwana, the southern portion of the continent, which had existed as a coherent unit since before Pangaea assembled, began its own long sequence of breakups across the Jurassic and Cretaceous. The first major rift within Gondwana opened between what would become East Gondwana and West Gondwana, roughly along a line corresponding to the modern eastern coast of Africa. This rift began to open about 165 million years ago. On its western side lay Africa and South America, still joined. On its eastern side lay Antarctica, Madagascar, India, and Australia, still joined to each other in a single eastern Gondwanan block. The rift widened slowly in the early Cretaceous into what became the western Indian Ocean. The eastern Gondwanan block, carrying its 4 modern continental fragments, drifted eastward and southward, away from Africa. This was the first great step in the disassembly of the southern supercontinent. At roughly 130 to 120 million years ago, in the mid-Cretaceous, a second major rift opened, this time between Africa and South America. It began in the far south, along the line that would become the southern Atlantic Ocean, and propagated slowly northward over the next 20 million years. Volcanic activity accompanied the rift, including the eruption of the Parana Atendica flood basalt province, another enormous eruption, leaving basalt plateaus in southern Brazil and in Namibia that are on opposite sides of the Atlantic and are the direct geological partners of each other. The southern Atlantic widened through the Cretaceous, a new ocean separating 2 continents that had, until then, been as joined as any 2 regions of modern Africa are joined to each other. The first animals to cross the widening gap had, by that time, begun to find themselves isolated on one side or the other. Dinosaur lineages on Africa began to diverge from dinosaur lineages on South America. The mammalian and reptilian faunas that had once been continuous split into 2 separate evolutionary histories. South America, isolated by the widening Atlantic, would develop over the next 100 million years a dramatically distinctive mammalian fauna, marsupials, unusual ungulates, giant ground sloths, that reflected its long period of isolated evolution. By 90 million years ago, in the Turonian age of the late Cretaceous, the South Atlantic connection between the Central Atlantic in the north and the Southern Ocean in the south was complete. Water flowed from pole to pole through the new ocean. The two Americas on one side and Africa and Europe on the other were for the first time in their history separated by open ocean from north to south. Of all the continents that came out of Gondwana, the one with the most extraordinary journey is India. India separated from Madagascar, which had itself recently separated from Africa and Antarctica, at approximately 88 million years ago. What is now the Indian subcontinent began to move northward across the Tethys Ocean, headed toward the Asian landmass, and it moved, as plates go, very fast. The normal range of plate velocities is 1 to 10 centimeters per year. Most modern plates move in the lower half of this range. The Pacific plate, probably the fastest today, moves roughly 8 centimeters per year in some sections. The Indian plate, during its northward journey in the late Cretaceous and Paleocene, moved at velocities estimated by some reconstructions at up to 18 or 20 centimeters per year. That is the fastest any continental plate has been reliably estimated to have moved in the geological record. What drove this unusual velocity is still debated. Part of the answer involves the subduction zone to the north, where the oceanic crust ahead of India was being consumed beneath Asia, and the pulling down of that crust exerted a strong forward pull on the Indian plate behind it. Part of the answer may involve thickness of the Indian lithosphere. Some analyses suggest the Indian plate was unusually thin, offering less resistance to being pulled, and part may involve a plume interaction with the adjacent Deccan hotspot, whose large flood basalts erupted on India's southern flank about 66 million years ago. The Deccan traps, erupting at around the same time as the Chicxulub impact, are one of the largest flood basalt provinces on Earth. They cover much of west-central India today, the plateau basalts of Maharashtra and Karnataka, and during their eruption at the end of the Cretaceous, they released climate-altering quantities of carbon dioxide and sulfur dioxide. Whether they contributed to the end Cretaceous extinction, alongside or in addition to the asteroid impact, is a live debate. What is not debated is that the Deccan eruptions happened on the northward racing Indian plate, and that they marked a major pulse of plume activity along India's southern margin. India reached the Asian continent and began the initial collision approximately 50 to 55 million years ago. The collision has continued without break ever since. It is what is currently producing the Himalayan mountains. The Himalayas are, by every measurement, the highest mountain range on Earth. Everest, at 8,849 meters, is the tallest peak on land. But Everest is only the most prominent of a vast system of peaks, with dozens above 8,000 meters and hundreds above 7,000. The total system runs for nearly 2,500 kilometers east-west, across the northern border of the Indian subcontinent, and it is the product of the ongoing continental collision between the Indian plate and the Asian plate. The Indian plate is still moving north. It is still pushing against Asia. The Himalayas are still rising at a rate of several millimeters per year, although erosion removes much of what is added. The Tibetan Plateau to the north of the Himalayas has been uplifted to an average elevation of over 4,000 meters by the same collision, the highest and largest high-elevation plateau on the planet, effectively a doubled thickness section of continental crust that has been compressed by the collision and pushed upward. The collision has also produced one of the largest earthquakes on the planet, the 1934 Bihar-Nepal earthquake, the 1950 Assam-Tibet earthquake, the 2015 Gorkha earthquake in Nepal. The slow compression of the Indian plate into Asia, accumulating strain that is periodically released in large seismic events, is one of the most active tectonic systems on Earth. India's journey from a southern fragment of Gondwana to the western cheek of Asia, across some 10,000 kilometers of northward drift in 88 million years, is one of the most dramatic single stories in the breakup of Pangaea. It is also, in modern geology, one of the clearest visible records of what happens when a continent moves. The collision has also transformed climate. As the Himalayas rose, they became a physical barrier to atmospheric circulation. The monsoon systems of South Asia, the seasonal rainfall patterns that watered the Indian subcontinent and much of Southeast Asia, are driven, in part, by the temperature contrast between the elevated Tibetan Plateau and the surrounding oceans. Before the Himalayas existed, the Indian subcontinent did not have anything resembling the modern monsoon. The mountains in the plateau produced it, and the monsoons, in turn, sustain ecosystems that support a very large fraction of the human population of the planet. The ordinary rainfall pattern that now feeds billions of people is a tectonic side effect of Pangaea's breakup. The Himalayan uplift also affects global weathering chemistry in ways that may influence the long-term carbon cycle. Mountains expose fresh rock to the atmosphere. Weathering by chemical reaction with carbon dioxide dissolved in rainwater pulls carbon dioxide out of the atmosphere and converts it over geological time into carbonate minerals. As the largest actively weathering mountain belt on the planet, act as one of the most significant long-term carbon sinks. There are geochemical models that link the cooling of Earth's climate across the past 50 million years, the cooling that led eventually to our current ice age conditions, at least in part to the enhanced weathering of the still-rising Himalayas. The climate you live in, the ice ages, the patterns of glacial expansion and retreat that have shaped the past 2 million years of Earth's history may have been driven, in part, by a single mountain belt that only exists because India collided with Asia after Pangaea's breakup. The collision also produced another quieter consequence. As India pressed north, it pushed crust eastward out of its path, producing the Great Escape tectonics of Southeast Asia. Indochina, essentially, was extruded sideways by the pressure of the collision. Faults running through Tibet and southern China accommodated the lateral motion. The geography of Southeast Asia, as we know it, the orientation of its rivers, the layout of its coastlines, the structure of its mountains, is the kinematic consequence of India's northward arrival. Pangaea's breakup